try and see if I can cover as much as possible today. We won't get chapter 6 finished, but we should get 6.2 and 6.3. That's my goal. The last section of homework is 6.4, 6.5. It's in one section, and I will be doing that with my other stats class on Friday. So what you're going to have to do is you're going to have to sometime between Friday and the beginning of the weekend, watch that video and catch up on the last part of chapter 6. So that's important that you do that, because there is going to be a test question from that last two sections, 6.4, 6.5, in your midterm. So on Monday, from 1 to 3, you're going to be doing the midterm. And one of the things, there are a number of things that you need to make sure that you do in the midterm. The first thing is that I need to see your video to make sure that there isn't any cheating going on. I can watch what you're doing. Once you've completed doing the midterm, you're going to send me a copy of your working. And you're going to do that because I have a program in Canvas called Adobe Scan, and it's a free program. You can download it onto your phone, either your Apple or an Android phone. And essentially what you do is you take pictures of your homework and it turns them into PDFs. And then you'll take those PDFs and you'll upload your working into Canvas. So not only will I get your test in WebAssign, I will also see the working, which I don't typically get to see. And I need to see that working because in WebAssign, if you do something wrong, and even if it's a minor mistake, you know, a plus should go, but a negative should go, it will give you 0 points. But if I see your working, I can give you partial credit for that. Now, there are a lot of questions where maybe that's not viable, but for every question that it is, you should show your working, and that's what I'll be looking for. So that's a big deal. You got to make sure that you are ready as best you can, and that your test is going to be on everything we've done up to and including chapter 6. So to remind you, you need to watch Friday's video to see the last thing. Your last question on your test is going to be from that section. So let's get started. Remember, we talked about Z-scores, and basically it's how many standard deviations you are away from the mean. And the formula is you take the data, whatever the number is, subtract the mean and divide by the standard deviation. And you can use these Z-scores for a variety of purposes. You can use them to compare two people's scores to see who did best, amongst other things. And this formula here is, if I tell you the Z-score, you can use it to figure out what the original data was, which is what's going on here. So, Chris, you've just arrived. I would watch the first 5 minutes of this video because I gave information about the test. I'll see if I've got time at the end to maybe repeat that. So these are the formulas. Mu is the mean, sigma is the standard deviation, and we talked about this normal distribution. The mean is in the middle, and it goes 1, 2, 3 standard deviations either side. When the mean is 0 and sigma is 1, it's called the standard normal distribution. Just like they stick this and they call it standard Z-score. So I'm going to pause for a second. There we go. So I've muted everyone, so you're going to have to hit the spacebar if you need to say anything. So what kind of things are we going to look at right now? Well, a couple of things in 6.2 that we haven't covered yet. So here goes. If I give you a relationship and I say, oh, we need a mean, don't we? Suppose I tell you that the mean is 30 and that the standard deviation is, say, 3.2. And I want to know what percentage of scores, or I just want to know what would this look like as a Z-score result. If I said X is less than or equal to 40, what would that look like in terms of a z-score? Well, you take this guy and you convert it into a z-score. So 40 take away 30 divided by 3.2. And let's see what that looks like. You go 40, you take away 30, you do that, you divide it by 3.2, you get 3.125. So there are a group of questions where they give you this guy and they say, what does it look like if you convert it in terms of a standardized z-score? Well, getting a raw data less than or equal to 40 is the same thing as getting a z-score less than or equal to 3.125. You'll also get, basically it's question 9, I think. You also get questions that say something like this. Now, you're taking this and you're going to convert it into the equivalent information using z-scores. Now, I'm going to keep the same mean and standard deviation again. If you want to do 30, if you plug it in here, I actually know the answer to 30. I don't even need to do a calculation. What's the z-score for 30? Yeah, 0. Now, 26, sure, I'm going to do 26. So 26 subtract 30, and then I'm going to divide that by 3.2, and I'm getting negative 1.25. Does that seem reasonable that it would be a negative number? And the reason it should seem reasonable, if your data is less than the mean, don't you get negative z-scores from it? And when your data is bigger than the mean, you get positive z-scores. Are we good with those questions where they give you this guy and you turn them into the z-score version? Right. Now, they have versions where they go the other way, so let's show you what that looks like. Suppose you were being asked to find z greater than 1.3, for example. Now, that would become x greater than. You can have equals if you like. It doesn't change the calculation. Now, how do I get that fella? Well, it's this formula here that I'm going to use. So I guess I'll put that at the side. It's the mean, 30, plus the z-score, 1.3, times the standard deviation. So mu plus z sigma. And on my calculator, I should be able to do that. It's 30 plus 1.3 times 3.2, and I get 34.16. And sometimes you get, oops, z less than 1, less than negative 2, in which case you just do this guy twice. So let's say a z-score of negative 2, that's going to be 30, take away 2 times 3.2, and that gets me 23.6. And if I want the other one, it's going to be 30 plus 1 times 3.2, and that's going to be 33.2. So this is just a skill building exercise where you're given information in terms of X and you have to turn it into versions of Z, or they give you information with Zs and your job is to turn into X's. And that's essentially what is happening in questions 10 of homework from 6.2. Let's go on a little bit further. It's happening in 11. Question 12 we've actually covered. And now we're on to the last part of 6.2. Imagine that we have the standard normal distribution. It's a very special distribution. The mean is 0 and the sigma standard deviation is 1. So that's going to be 0, that's going to be 1, that's going to be 2, that's going to be 3. This guy's -1, this guy's -2, this guy's -3. And we are going to be asked questions like, they'll phrase it various ways, but this is one of the ways. What area is to the right of z equals 1.33? Or what area is to the left of, say, z equals 2.1? Or what area is between things like that. So what you've got to imagine is if you looked at this shape, theoretically at least, this shape goes on forever. But the area, the total area, is just 1. Or if you want to think of it as a percentage, it's 100%. If I wanted to know the area to the right of 1.33, 1.33 is roughly about here. And the area to the right is how much that is. Well, it's not 1. It's not even 0.5. Wouldn't the right-hand side be 0.5? But it wouldn't really be a good idea to try and guess, because it'd be very hard to be accurate. Agreed? I mean, I could guess it's about 0.2, but it's a really bad, rough guess. So wouldn't it be nice if there was an easier way, some software, that could answer these kinds of questions? So I'm now going to show you that software. It's in Salt. So let's click on it and let's show you. Now, although there is a lot of questions, and there's a lot of questions, they are not, they don't take that long. Right, so right now I hope you're saying sketch the area under the standard normal over the indicated interval and find the specified area. Well, I've already drawn the picture, right, on my piece of paper, right? So you don't physically need to do that on the computer. Let's find the area to, say, the left of, no, there we go, to the left of -1.33. So you hit this button called solve, boom. And what will appear by this guy? Now we've got the mean 0, we've got the standard deviation 1, and I want to the left of, I forgot what the question was. I want it to the left of -1.33, left tail, and you make this number here -1.33. Now, can you see it's actually drawn the picture? Can you see that's roughly where it would be? Everything to the left. And that particular fella is that number there, 0.09176. Now, suppose I wanted to know to the right of that. Well, you hit the right fella. You go up here, and, well, I've actually got it. Can you see the answer? Yeah. Suppose I wanted to know to the right of 2.5. Well, okay, 2.56. You see, once I put the answer in here, doesn't this one automatically update? And also, do you notice that the picture, how small that is? Now, if I convert that to a percentage, 0.005 is very roughly 0.5%, 0.5%. So only 0.5% of all Z scores are bigger than 2.56. Now, if I change that number a little bit, let's make it a nice round number. Well, what about 0.6% is less than 2.5? Can anybody remember how big does a Z score have to be an outlier? Great, 3. So if I go here and I make this 3, do you notice in the picture there's hardly anything left in the curve? There's a little sliver. Can you see that the number is tiny? 0.001, which is what, 0.1%? So can you see that an outlier is like a 1 in 1,000 person? A very unlikely, very unusual result. Are we good with this piece of software and how it can be used to find areas to the left or to the right? Let's do a between. That's both tails. Now I want it to be between, so I hit that one, right? I want it to be between -2, rub this guy out. It's having issues. Stop having issues. And 2. There we go. There we go. Can you see -2, that's a big chunk in the middle? Wait a minute, isn't a z-score of -2 2 standard deviations away from the mean? What percentage was 2 standard deviations away from the mean when we told you on Tuesday? What would it be? Right. Does that guy there look darn close to 95%? Do you see that 95% wasn't just a made up number? It's actually in the diagram. You can see what it is. How much was 1 standard deviation away from the mean? What percentage was that?
68.
So if I change this to -1 and I go next door to it and I change this one to 1, shouldn't I get, and guess what, I did. Isn't that darn close to being 68%, at least the nearest whole number? So remember that 68, 1 standard deviation away from the mean, 95, 2, and 99.7 was 3. Remember that one? 3 standard deviations away from the mean, 99.7. It's all in front of us in this table. Everything you could possibly want is kind of there. So can you imagine that all you're going to do is hit that button and basically do to the left, to the right, or a between? Do you want me to do another one of these just to show you how the salt thing works? Or do you feel comfortable about hit the button and type in the numbers? So if you do this well, wouldn't each question take you about a minute? Right. So although there is a lot of questions, they are for the most part pretty much do what you want. I guess I should finish on one just because I can. Now this is me doing I don't know, -28. So negative, better write this down, -2.04 and -0.21. So I'm going to hit salt. And now I'm going to go between. And on one side, I'm going to type -2.04. And on the other side, I'm going to choose the second number, which was -0.21. Didn't hit my decimal point. And the answer is what, about 39%, 0.39. What I've done. So you might think, what's left? Well, there's still a fair amount left. In these questions here, you just use salt. Do you know that picture that was to the bottom right? One of these will be the same picture and you just say it's that one or you say it's that one, right? So that in itself isn't particularly different. I'm just scanning through in case there's anything I have missed. No, I'm good. If you're comfortable with that piece of program in salt that does all these Z bigger than, Z less than, or Z betweens, then we can move on. Do you want me to do any more of those questions, or are we good to move on? I get one shake and yes.
I think we're good.
Oh, okay, I'm happy with that, but I can't guarantee that we're in that same boat. So we can now start our new chapter 6.3. And there's a lot of overlap in 6.3, which is kind of nice. In question 6.3, we are going to look at distributions where the mean and the standard deviation are not 0 and 1, right? Just any old normal distribution. So for instance, if I wanted to draw what this would look like, it would go 30, because that's where the mean is. And since the standard deviation is 5, won't I go 1, 2, 3, and go up in 5s? And 1, 2, 3, and that would be go down in 5s. Now they're going to introduce what's the probability, which might seem different from what's the area, but technically it's not. For instance, if I wanted to find what's the probability that I choose one person at random, it's always one person at random in these questions. Okay, let's pretend this is a test in a class, right? What's the probability I choose one person at random and they get a grade of 37 or better? Now, my picture, roughly 37's about here. So isn't 37 or better that guy? Now, the area of that shaded thing is exactly the same thing as the probability, right? So the percentage of people bigger than that score, it's the same thing as picking one person at random and they are bigger than that score. So we just need to figure out how to find this area. And it might not surprise you that salt is going to do that. So I'm now going to show you how we could use salt in this question. So I'm just going to use this button to do it. So I'll hit the button. And you just have to change some information. The story is now going to have a mean of 30. That's what the average in the class was. And the standard deviation I told you in that story was 5. And we want to know right tail, right? People who got bigger than something. And I want to know what percentage of people got bigger than 37. And there is your answer, ready to go. As a decimal, 0.08. As a percentage, 8%. So the chances that you choose somebody at random from that class and they got 37 or more in the test, that's going to happen about 8% of the time, right? 0.08. That makes sense? Okay, what percentage of the class are going to get the average or bigger? Can you see the picture? And the answer is exactly what you thought it would be, isn't it? 50%.
Yeah.
Somebody, let's pretend the story went like this. Somebody in this class got 48 in the test. Maybe the test is out of 50, right? They got 48. Is that exceptional, right? Are they an outlier? Well, it shouldn't be too hard to figure out. 48. Do you notice the Z score is bigger than 3? So yeah, they're an outlier. If you want to know how likely that is, God in himmel, look at how small that is. 0.302. That's about one in every 5,000. So the chances are that nobody in that class got that score. If they did, they were really on their own, right? Nobody else would be even near them. Now I'm going to come back to that guy in a minute, but I'm going to give you some more questions where we deal with that kind of situation. I'll go to one of my, should click on this a bit better. I'll go to one of my favorite concepts, IQ. The mean of an IQ is 100 and the standard deviation is 10. That's actually correct. That is what the mean and standard deviation of a typical IQ test is. Now, if I wanted to draw a visual picture of what that would look like, 100 people, right? An IQ 100 is exactly in the middle. Then you go 110, 120. By the time you get to 130, there's not many people left with a bigger IQ. You can go 90, you can go 80, you can go 70, right? And it goes the other side. So the kinds of questions you're going to be asked are things like, I'll write this sentence down once. If you choose one person at random, what is the probability of, and then ... Right, so what's the probability then that you get a person whose IQ is bigger than 120? You could get, what's the probability that you get someone who has an IQ less than 80? You could get, what's the chance that you get someone who has an IQ somewhere between 130 and 120? Or any other permutation you want of these guys. Now, every single one of those, we are going to find its probability. And we're going to do it to 3 decimal places, because very often that's the kind of accuracy that they want. So I got everything I need here. So this is going to disappear in a second, because I'm going to zoom over to salt, which is going to show us how to, or will allow us to do it. Here we go. Now, the mean of IQs is 100, so I'll change that to 100. The standard deviation is 10. And my first question was somebody who gets an IQ greater than 120. And the chances of that happening to 3 decimal places are 0.0227 rounds up to 3. So about 2.3%. So if you ever get your IQ tested and it's bigger than 120, that'll put you in the top 2% of IQs. Let's do a less than, right? Well, if you want to do a less than, you hit that fella. And now this number changes, and I want to know, I want to know less than 80. And the answer happens to be 0.023. And now I want the between. And it has to be between 120. That's not right. 120 and 130. And the answer is 0.021. Can you see that I could probably answer any other version of that question you could possibly want? Couldn't I find out what percentage of people have an IQ bigger than 130 or less than 82 or between this number and this other number. All of them are possible. Very powerful piece of software. These are the results I've got. 0.023, 0.023 again, and 0.021. I wonder why these two are identical. Let's see if we can find out. If you take this guy, that area there is 0.023 because the area exactly matches the probability. On the other hand, if you do 80 and you go this way, that area is also 0.023. Is there any explanation for why that happened? Was it coincidence or was there something going on here? Any ideas why they are equal?
Because they have the same z-score, just one's negative, one's positive.
Yep, that works for me. Just visually, isn't that the same size as that? It's the same shape, it's symmetric, whatever you want to call it. Yeah, same z-scores, 1 plus 1 minus. Symmetry, all good. Now, suppose I gave you a question that went like this. Oops. And I'm back to the z-score guy. So this is, well, this is just a special case, isn't this? A special case of these guys. Right? Just when the mean is 0 and the standard deviation sigma is 1, it's called the standard normal. Suppose I told you that 30% of the area was to the right of Z. You should be able to decide which one of these two has to be true. So I'm going to put a number here, it's called Z, but wherever I put it, 30% of the area has to be the right of Z. Is that Z going to be a positive number, so it's over here, or is it going to be a negative number, which means it has to be here? Any takers?
Positive.
Correct. Why?
Because if it was negative, then there'd be a lot more in front of it.
Yeah, that'll work. If I put my pen right in the middle, isn't 50% to the right? If I want only 30% to the right, don't I have to move a little bit here to about here somewhere probably? Yeah. It's an easy homework question to answer, isn't it? You either hit the top dot or you hit the bottom dot, right? But there's a little bit of thinking behind it. Now, next question. Suppose you have a load of data and you are wondering, does this data fit the normal distribution? Is it bell-shaped? And various other names that they use for that. And you could eyeball it, but that's not really a good idea. And the reason why eyeballing it is not a good idea is, let's take this example. Here's the question for it. If you took all this data and you made histograms of it, it would look something like this. I don't even like that blue line. I wish it wasn't there, but regardless. If you looked at this histogram and you were saying, does that have that bell-shaped curve that we're hoping for? You're more likely to say, no, it doesn't. And the reason is, I would suspect, is that when you look at it, doesn't that rectangle look big and it should be lower? This one here. Does it look like it's got more on one side than it has on the other? Looks like there's only, what, 4 here, but there's 5 rectangles there, you know, this kind of thing. And we are hardwired to do many things, but 2 major things. Our brain is hardwired to see patterns, and our brain is also hardwired to see when things don't fit. And it's probably for way back in the day, if lots of things couldn't eat you, isn't it a good idea that when you look across the savannah, that you notice that bump there doesn't look like it should be there? Oh, that bump there could be a lion that's going to eat me, right? So your brain is hardwired to recognize things that don't fit. Your brain's also hardwired to recognize patterns. Unfortunately, if you use this rectangle, you are more than likely to decide that this data is not normally distributed, which means we can't do all the cool stuff that we've been doing, like what percentage of people would be bigger than this or less than that, right? All those kind of cool things won't be possible if it's not normal. But actually, it only needs to be approximately normal. It's never going to be perfect. Real life data is never perfect. So how do we fix that? Well, right next door to it, you don't ever need to know how to plot these, but let me tell you how they're created. Along this set of data here, this is the raw data, and this is the Z-score that they got. So see that number there that says 29, which is here? 29 had that Z-score. So you plot each number with its Z-score, you know, like an X and Y. And do you notice that that is pretty much a straight line, isn't it? That's what normal distributions look like. When you plot the data against their Z-score, does it look like a single straight line? If you can say that, you are pretty sure in saying this data is normal, and you can do all the cool stuff. Now, what would it not look like? Well, if it wasn't normal, can you imagine the dots went kind of flat and then they curved up and it looked like an S shape? That wouldn't be normal. Can you imagine data that went up really fast and then it kind of leveled off at the end? Looked like, that kind of shape. That would not be normal. But is it a single straight line that's going up without much variation? The answer is yes, it is normal. And if it's normal, you can do all those kind of things. And I seem to have picked up some answers which I don't want because they distract the heck out of me. Are we good so far? So the next, it's still not updating. Darn it in space. Go away solution, don't want you. Okay, right, I should be ready for our next question. Right, this is question 5. You're told that the mean is 8, mu is 8. The standard deviation is 6, so I'm writing that down because it's going to disappear in a second. And we would like to know what's the probability that you get a score, an X between 5 and 14. And that's pretty standard kind of question. So hit that guy. Bring it up here. Now the mean here was 8. The standard deviation in this question was 6. We were going to do a between, and the numbers were 5 to 14. 5 to 14. And the answer I got was 0.05, sorry, start again, 0.53281. And then you go here and you type in to 4 decimal places this time. 0.5328. That's how easy that's going to be. Are you happy that this is kind of very similar to what we've already been doing? The only difference is we have to put in a mean and a standard deviation each time because they keep changing. And I went through a whole load the last time really fast, and you said you were fine with it, but you don't need to be fine with it because I say that. We should do some more, shouldn't we? Do you want me just pick one at random and do it? Okay. This is question 10. The mean is going to be 22. The standard deviation is 3.4. What's the probability that you choose someone at random and they are greater than or equal to 30? So here goes. 22, 3.4, greater than or equal to, so that's a right tail, and greater than or equal to 30. And the answer is a very tiny 00931. And to 4 decimal places, that's all you write down. So I'm hoping that you can go through all the questions, essentially up to question 11, doing that, right? Do you feel comfortable if I said the mean is this number, the standard deviation is that number, what's the probability that you get it bigger than 10, less than 8, or between 4 and 7? Those kinds of questions. So moving on, still in this section. What's the next thing going to look like? Well, it's kind of the reverse of what we just did. I want you to imagine, back to my IQ again. And it looks something like this. And I tell you that I'd like to know what IQ I need to be in the top 20%, right? I'd like to know what IQ would that be. Now, 20% is actually on the software going to be called 0.20, right? So far, so good, right? 20% is 0.20. And we are going to find that missing IQ. Now, it's pretty obvious it's bigger than 100. Any guesses? Logan, I'm picking on you. Give me a guess. Would you think you need to be in the top 20%? And it is a guess. Can't hear you.
110.
Okay. Chris, give me a guess. Can you hear me, Chris? There we go. Give me a guess. Give me a guess. And it is a guess.
Let's see, 105.
Okay. Who are
Like a Price is Right type guess. Yeah.
It is. It is. To me, it's the same. I'm just saying. I know. The only thing I know is it's bigger than 100. Would you agree? We can all accept it's bigger than 100. After that, it's really guessing.
Because I know you're into trick answers, and so.
Oh, I'm not trying.
I'm thinking it's closer to 100. Yeah.
I don't know if it's closer to 100. I honestly don't. I find these are really just. I have to trust the software, right? There's not. I've got a mental picture of good guesses. Bailey, we'll give you the last one. Give me a guess. Can you hear me, Bailey? Give me a guess. Last chance. She's texting it maybe. Okay, I'll have to do it myself then. I'm going to go, not because I know the answer is 115. I just figured out it'd be a good idea to, pick a number a little bit bigger than the other two. Let's find out who's right. I'm going to take this information and that number, and we are going to show you how you do it on Salt. So you can imagine this program's going to be a pretty much, you're doing a lot of your answers on it, right? It's going to be a lot of questions. So I'm hitting the sort button. Here we go. And in this case, it's going to be 100 for the mean. This case, it's going to be standard deviation of 10. That much we've got. And now, do you see the number there that is where the answer used to go? That's where we would read our answer. That's where I put the 0.2 in. And the correct answer was about 108 to the nearest whole number. You're good at guessing, Logan. You were a close second, and I was last, right? So can you imagine then that we can find what IQ score puts you in the top 10%? Could I find the IQ score that would put me in the bottom 5%, right? The lowest 5% of IQ. You can't see me drawing this, but I'm actually drawing a little picture and I'm putting 5% in. Well, let's see what I would need to change. If I'm talking about the bottom 5%, don't I have to hit the left button? Right, because it's over here. And the decimal that's going to go here for 5% is 0.5. And you need to have an IQ, if you are in the bottom 5%, you need to have an IQ roughly about, if I round it off, about 84. Do you feel comfortable about how this process is working? How we're using salt in a kind of, here's the answer, tell me what the X is kind of way. Rather than, here's the X value. Hold on a second. What is it? Come on. I'm teaching. Bye-bye. You go enjoy it. Come on. Come on, guys. Come on. Can you stay there? Okay, we're done. That was my dogs were requiring attention, I guess. Are we good on this type of question? Because I want to do one more, but if I need to, I'll do 5 more or 2 more or whatever other number you like. Are we good? Okay. So can you, I should switch over to, I may already be on that. Oh, I'll get a chat. Okay, Bailey's catching up. Where the heck am I? Here we go. So we can find a Z score that 80% is to the left of Z. We could find a Z score 88.1%. We could find one of these guys. Okay, let's pick one. I'm on this one. Find a Z score such that 6% lies to the right of Z. Okay. 6% to the right. So you hit the sort button. Since this is a standard norm, do you see it's 0 to 1? And I want 6%. I've almost got it set up here. Now, all I have to make sure here is that the question that was being asked, well, it's to the right of Z, so actually it's not the question. That's to the right, and the number I want is 6%. Okay, now we got it. The correct answer, 1.5548. To 2 decimal places, 1.55. And what did the picture look like? Let's see. It looked like a little bit to the right. And that would mean it would be that picture, right? A little bit to the right. I'm about to move on to the next part of this process. Are we good? So you don't need to see more than just a couple. You will find out, I'm sure, later whether that works for you. So here's our next question. This is 17 from the homework. A person's blood glucose level and diabetes are closely related. Okay. Let X be a random variable that measures in milligrams of glucose per deciliter, bracket, that's 1/10 of a litre of blood. Suppose that after a 12-hour fast, the random variable X will have a distribution. So here we go. Mu equals 87 and sigma is equal to 27. Now, it goes on and tells us some stuff that are interesting, but not necessary for the question. What's necessary is the mean is 87 and the standard deviation is 27. We're being asked to find what's the probability that someone will have a glucose level greater than 60. The next one is going to be less than 110. The third question is between 60 and 110. And the last question is greater than 125. And if you get a greater than 125, then you're borderline diabetes. So I guess that's the test for diabetes, right? They take your blood sugar level, and if it's a number bigger than 125, hey, you might have diabetes here. At least we should look into it, see if we can help. So I'm about to hit the stop button. But I don't know about the upteenth time. In this story, the mean has now switched again. It's a number, it's 87. And the standard deviation is now 27. And we are looking for what's the probability. So we're back to using this fella. And the first one is greater than or equal to 60. So I'm going to hit the right tail. And greater than or equal to 60. And the answer we get is 84, right? So that's 0.84, 84%. Let's say we want to do less than 110. Well, that comes out about 0.80. Let's do a between. We want this number is 60. And this number over here, you'd like this number here to be 110 according to the question. And the answer you get here is about 64. And greater than 125. Which is about 0.08. Okay, let me return to our written stuff. See what we can get out of this. Right, if you look at the blood sugar level for the typical adult, using this mean and standard deviation, about 84% chance that you have a glucose bigger than 60. There's a 80% chance that it's less than 110. There's a 64% chance that it's in this range, which is pretty much going to be pseudo-normal range, and about 8% chance that you have a value that's bigger and therefore would be considered borderline. So if you were having a blood sugar level kind of scale, at this end they'd have 125, and that is not good because borderline diabetes, BD. Right in the middle, you'd have 87. If I do a quick calculation, that's 13, and add 13 to that, it's 38. Take away 38 from that, and you get, I believe, 49. So I'm not quite sure what it is at that end, but if your blood sugar level is too high, you're borderline diabetes. I think you're diabetic if your glucose level is really low as well, isn't that? It goes up or it goes down. That's the problem. It's not stabilized in the middle. But these are the key numbers that you want to look for. If somebody drops below that, and don't you give them something like a candy bar or something, or they keep one? You know, they try and get their glucose level up. And I don't know what happens in that. That's if they've ate too much sugar, they get kind of overdosed on the darn stuff. But now we've got a way of figuring out how to put boundaries on certain extreme values. And that gives us a way of saying that number isn't healthy. That number there, borderline. That number there, probably also borderline. My usual question. Have we any questions? Are we good with that? Oh, Bailey, cool. Thumbs up, works for me. Let's do another blood one, because I know some of you at least are in the medical field. I can't pronounce that word. Or at least I tried with the other class, and I think I failed miserably. But I'll take a volunteer. Anybody want to pronounce P-O-R-P-H-Y-R-I-N? Because maybe if you've done some of the nursing stuff, you've actually heard that word before. Any volunteers? Chris, you try to say it.
How do you spell it again?
P-O-R-P-H-Y-R-I-N.
P-O-R. Is it Porphyrin? P-O-R-P-H-Y-A-N?
I don't know what screen you're on, so I'm going to put it on the main screen, and you can just read it. Here it is. I'll make this a little bit bigger because I know how big your screen is. There it is.
All right. Porphyrin?
That'll do for me then.
Yeah.
Porphyrin is a pigment in the blood protoplasm.
Yeah,
And
it sounds like it would be like a pharmaceutical. Like I could see a commercial for porphyrin.
Huh. So yeah, it's the kind of thing that they give to this. This particular thing is a pigment in your blood protoplasm. So it's actually in your blood rather than a chemical you take. But it could be in another world. And you also get it in other bodily fluids. And it's significant in body energy and storage. Okay, never heard of it, but evidently this is a big thing. And if it doesn't work right, I guess there's diseases associated with not having enough or having too much. Now, since it is significant in body energy, I'll make this up. If you don't have enough, won't you be lethargic and tired and kind of run down? And if you've got too much, won't you be like a hyper kid who's bouncing up and down like a yo-yo and you almost have to tie them down? So let X be a random variable that represents this number. And in healthy circles, right, people who have what a typical person would have, the mean for this thing is 39. And the standard deviation for it is 14. So the only two key numbers you really need for any of these questions are those two numbers, right? Tell me the mean and tell me the standard deviation. And can I tell you everything else that I would want to know just from that and using Sol? So I'm going to just do two of these. We're going to find if you choose a person at random, what's the chance that they get a level between 16 and 60. This is question C. 16 and 60. So I'll hit that guy. I'll come over here, and I might have to reduce this a little bit. I can still use it. Okay, the mean is 39. And the standard deviation is 14. And we want a between. So a between is over here. And I want a between 16 and 60. So 16 at one side and 60 at the other. And, well, I'm there. Oh, I put it in the wrong place. 16 and 60. And the answer is 0.88299, which if you round it off to 4 decimal places is 8830. So about 88% of adults, based on that picture, isn't it roughly the middle 88%, right, where normal values are, would have that level. Now, I believe they had an extreme case. Yeah, if it's more than 60, they can use this, the amount of this porphyrin that you've got, and it indicates either an infection, anemia, or something that they would be concerned about. So it's got to be more than 60. So let's see what more than 60 looks like and what percentage of the population that could work with. So right tail is for more, and we want this number to be more than 60. And that comes out as a kind of 6 going on 7% of the people would be detected as that. Now, normally what they do with a lot of blood tests is they don't just look at one and, you know, that's it. One number tells you them all. It's all bank of things. So they look at that as an important marker. But there are other markers. Can you imagine they might also take your glucose level, they might also take your blood pressure and your body temperature and so on. So that, try to put this together as if I was a doctor, which I certainly am not. But can you imagine if you had a slight temperature and this number was bigger than 60 and you had a higher number of white blood cells in your bloodstream, if you put all 3 of those together, that would make me think you have an infection, right? Because those are the kind of things that go with infections, right? Whereas a different combination of things might be telling them your liver's not working as good as it used to, right? There's something not quite right about your liver, or there's something not right about your heart or your thyroid. Your thyroid's a killer. You know, your thyroid produces all sorts of body enzymes and proteins, and if that darn thing starts acting up, it's a bit like, what's the analogy? Can you imagine your oil pump in your car's not working great? Doesn't that just cause a whole load of weird results all over the place? Not a good thing to have go wrong with it, trust me. Are we good with that question as well now? Tell me the mean, tell me the standard deviation, and we can go hunting for any kind of percentage that you like based on that. We're actually doing faster than I thought, which is good. So if you're okay at this, I want to go on and at least touch on the next section. Maybe I know I won't get it finished because there's too much in it, but at least get a start on it. Are you good with the rest of these questions? You feel you could do them? Then we are moving on now. Let's go. I got a thumbs up and a nod. I'm not a clue what's going on here. There we go. So it'll take me a few settings. Thank you for putting your thumb up, Victor. So here we go. Give me just a few seconds to kick this up. In case I forget, will you say hi so that you get attendance for today? Just take me a few more seconds to get this all set up. With a bit of luck, be good to go shortly. Oh, darn it in space. It's not doing what it needs to do. Okay, I'm going to close it off. Try and do it a second time. Do you know why I talk to myself? Any guesses? It's the only way to have an intelligent conversation. At least one of you got that joke. Okay, so it should be ready now. I just put up the answers there, it'll make it a bit quicker. So, section 6.3 deals with what's called the sampling distribution. We'll get to the intro part of that. That's probably as far as I think we'll get today. So, which is essentially we're going to get the 6.4 part done. I won't really get, who knows, maybe. I probably won't get to 6.5. So let's start off with the guy that we touched on, I think in week 1. It's a long time ago now. We're going to look at what's called a simple random sample. Very often you cannot collect all the data from a population, right? Population's everybody. You just don't have the money or the time or the manpower or whatever else, and it can't be done. So what you very often do instead is that you collect a small group of people called a sample from the population. And the best version of a sample is called a simple random sample. And it's defined in this way. Simple random sample, SRS for short, has the property that every member of the population has an equal chance of being chosen for the sample. I don't want to have to write that anymore. Right, a simple random sample then. Imagine you were trying to find the average age of people who lived in Bremerton. Right? Now, what you might do is that you might do a sample of 100 people. And we typically use ler n to represent the number of people you use in a sample. And let's assume that it's a simple random sample. That means anybody in Bremerton could have been picked. You picked 100 of them, right? And you came up with a mean. And the mean height We call the mean of a sample this X with a little line above it. Can you remember how you say that out loud? You say X bar. So the mean of a sample is called X bar. And for this 100 numbers, can't we also find the standard deviation of a sample? So of that sample of 100 people, we can do that. And we typically call it S. So far, so good. Now, this is a sample. All of this is talking about things to do with a sample. Let's look at population. Oh, curve the corner. Population. Doesn't the population of Bremerton have an average age, right? It has a mean. Right? We call that guy mu. Remember, that's how you pronounce him. Yeah. Does the population have a standard deviation, right? You imagine there's 32,000 people in Bremerton, right? Isn't there a standard deviation for that? And the standard deviation, I'll just call it SD, is that there, which we pronounce as sigma. Now, suppose I had a sample of 100 people and I got the sample mean. And let's just pretend that I found the right answer, because Bill Gates gave me enough money and I actually found every single person who lived in Bremerton and I got their age. And so I know what mu is. Mu is 31, because I've just decided it is. If you take a sample of 100 people and you find the average of them, do you expect that sample to be exactly 31? If you randomly just pick 100 people from Bremerton, add up their ages and divide it by 100, do you expect to get 31? That's the question. What do you think? I'm getting old here. I can feel my synapses drying up.
No, the answer is no.
Thank you. You might get 32.5, right? If I did another different sample of 100 people, do you think I'm going to get 32.5 or even 31? No.
No.
Couldn't you the next time get 30.8? Because samples don't tell you the exact answer for the population. Don't samples just give you an estimate, a kind of ballpark figure? And if this was my only sample, I would be saying it's somewhere around about 32.5, give or take, 4 or 5 years, right? And if I got this one, I might say the same type of thing. Right? Now, here's a different question, and it is a different question. Suppose my sample size was 10,000 people. It's still not everybody in Bremerton, but it's a big chunk of people in Bremerton. Do you think this answer will be exactly 31?
No, but it'll be closer to the mean.
That's
than a
exactly
smaller
what I was
sample.
hoping to hear. Yeah. Now, what's that reflection? Well, isn't it a kind of truism? Isn't the bigger the sample, the more likely you are to get an average that's closer to the truth? So you might get 30.95. Maybe not quite 31, but darn close to it, right? So the idea behind samples is that if you choose a small representative group, you will be able to use this number as an estimate of this number. Not that you're saying this is equal to that, but you are at least hoping that it's close to it. The second truism is that if you pick another 100 people and do it again and again and again, won't you get slightly different answers every time? And won't all of those answers still be estimates of the truth, which is 31? And if you do a really big sample, in general, won't you expect the mean of the sample to be very, very close to the true answer? Are we cool on that? Now, terminology. Some things are called statistics, and some things are called parameters. If the number, and they're both numbers, if the number came from a population, then we call that a parameter. If it came from a sample, that number, we would call it a statistic. So let's show you some examples of sample statistics. Is an X bar an example of a statistic? Isn't that just the mean of your sample? Isn't S an example, right? Oh, by the way, S, the standard deviation of your sample. That's an example of a statistic. What would the population parameters look like? Well, isn't mu, the mean of the population, a population parameter? Isn't sigma a parameter? It's a population standard deviation. Now, there's one that we haven't done yet, but I'm putting it in. And it's called P, and this guy here, we call him P hat, because he's got a little hat on, right? You know, sometimes you go and ask people, what percentage of you are going to vote in the next election, right? You don't care who they vote for. You just want to know, are you going to vote, right? That would be an example of a population proportion. So these are called proportions. So I might ask 100 people, are you going to vote in the next election? P hat is what my sample said. I asked 100 adults and 72 of them said yes. So P hat would be 72. This number is the population number. Isn't this actually, once the election's over, what percentage of adult Bremerton people did in fact vote? And you see that each population parameter doesn't have an equivalent statistic that does the same job. So I ask 100 people and 82% say they're going to do it, and in real life it ended up being 72. That would be an example of a statistic and a parameter doing the same job. We good? Any questions so far? Okay, move on. Now we're going to look at a guy called the sampling distribution. This is something that a lot of people, until they get used to it, find it a little bit hard to get their head around. So I'm going to use the Bremerton story. And I'm going to imagine that I do lots and lots of samples of size 100. And this number line here is kind of representing the kind of numbers that I might have got from calculating the mean of my sample. So I do it once and the answer is 30, right? I do it another time and it's 29.5. I do it another time, it's 32. I do it another time, it's 31.5. And I keep doing it for hundreds upon hundreds upon hundreds of times. Can you imagine all the different values for X bar I could get? This is what we call the sampling distribution. Do you notice it's got an interesting shape? It's bell-shaped, it's mound-shaped, it's normal distribution shape, same things, right? Do you notice a couple of other things, even if I've drawn it badly? Do you know the highest place in that shape would be at 31, where the population value lives? And won't you get lots of answers very close to the right answer? But won't you sometimes get some really weird ones which are miles away from the right answer? You know, just sometimes don't you just get a really, for want of a better word, a really unlucky sample? And you add them all up and the average age comes out to be 40. How did that happen? Well, you got really unlucky and 5 people, 90 plus, all ended up in your sample. Can you imagine that could really screw up your data? This is called the sampling distribution. It has a mean and it has a standard deviation. And its mean is the same as the population mean. So in this case, 31. And its standard deviation. Well, that's where it gets a little bit tricky here. The standard deviation that you typically get from this is this guy. Sigma, which is the population standard deviation, divided by the square root of n. And that's probably, of all the things, that's probably the weirdest. Can you just trust me that that's what you get? That this distribution of all the samples, called the sampling distribution, has a mean the same as the population mean, and it has a standard deviation equal to this. So can we pretend that not only do I know the population value, but for somehow or other, I even found out that sigma was 5, right? So if that was the case, wouldn't this be 5 over the square root of 100? This would be 0.5. So the sampling distribution has a much smaller standard deviation than the population one. Does that seem unreasonable? Or does that seem okay? I mean, it's true. I'm not trying to catch you. It is true. But does that seem intuitive that if you take 100 people and average them out and you do it lots and lots of time, that you end up with a much tighter range of numbers than if you just randomly picked one person at Bremerton and got their age? Right, let me try and convince you it's true. if I picked one person in Bremerton at random, couldn't I pick a 90-year-old person? There's a few out there, right? I could have picked them. Great. What's the chances that you ask 100 people in Bremerton and the average is 90? That would never happen, would it? Well, what is that indicating? That's indicating that this thing has a very small variation. Right? If you take 100 people and average them out, there ain't a lot of variation going to happen there. Because if you get a couple of old people, don't you also tend to get a couple of young people and they balance out? But when you choose just one person, you don't have that balancing out. Don't you just get what you get? And so this is correct. We can use this to do a test. So yeah, it's going to have to be the last part for today. I've got things to do, but here goes. Let's suppose that we already know that the, oh, how shall I do this? Yeah. That we know that the mean IQ is 100, and we know that the sigma is 10, right? That's IQs. I'm picking IQs. And we are going to use a little test. So we went to Scotland, and we think Scottish people are cleverer than the typical IQ person. Now, you would think IQs are universally the same, but they're not. Do you know some countries have a higher IQ than others? And they're not in Europe or Asia or anywhere else. They're everywhere. I mean, you could go one country in Asia and it's high, and the next country it's lower, right? It's just the way things are. There's nothing particularly racial about it. I mean, the French could have a high IQ and the Italians don't. I mean, it's minor, like it's a point difference, but it's different, right? So we did the Scottish one, and we did a sample of 1,000, which is a lot of Scottish people. And the IQ we got was 101. So the average IQ out of 1,000 Scotsmen is 101. And now we're going to find out, is that exceptional or not? Well, I'm going to create the sampling distribution. Its mean is this guy. And its standard deviation is sigma over the square root of n, and that ends up being 10 over the square root of 1,000. And I'm going to do 10 divided by the square root of 1,000, and that ends up being 0.316. And now I'm going to use these two numbers and my little guy that looks like that, and I'm going to find what's the probability that you can get somebody with a mean 101 or bigger. We're being generous to the Scottish people, right? What's the chance that you get 101 or bigger? Well, you go to, and I'm going to have to jump about for a little bit, so if you hold on, we are going to find basically how rare that is. And I'm just going out and in, hopefully I can find the darn thing. Here we go. It's still loading up. It has loaded up good. So I'm going to share it, and we are going to check how likely that is to happen. Now, Hopefully you're looking at a salt button right now, right? Okay. If the chances that you get a mean bigger than 101 are really tiny, isn't that evidence that that didn't happen just by luck, that Scottish people's IQ are actually bigger than Americans, say? Use salt. Now, it's a normal distribution. The mean is still 100. The sampling distribution is a little bit different. It was at 0.314. And we want to know what's the chances you're to the right of it. And this number is 101. And there's my answer. It's a 0.00072, which I'm going to convert into 0.072%. And I am now going to pretend that this is true so I can be a show off. The chances that you get a sample of 101 out of 1,000 people, if it was the same as the rest of the world, would only happen randomly, 0.072. That is so small. What that means is that this isn't from here. This is so small, this is actually proof that Scottish IQs are bigger than 100. So you can test any kind of hypothesis, is a fancy word for it, based on using the sampling distribution. You go and collect a sample and you look at that sample and you say, hey, is this sample within the normal variation that you would expect if this was true? Well, if that's the case, shouldn't this number here be pretty big? Now, pretty big doesn't need to be 80%. You know, pretty big can be 5%, right? It's big enough that it could happen. But could something as small as this happen? So rare, it's probably not the case. It's more likely that the IQs are bigger. And that is going to have to be us for today. So will you remember, pardon me, to look up Friday's lesson and also look at this Saturday or Friday maybe, if I get a chance I'll put it up, on how to upload your working into Canvas. And I'll also have a video on how to use Adobe Scan, how to actually use your phone to take pictures and turn them into PDFs. That is me. Any questions?
What
Yes.
is that for?
What? Oh, the new Mr. Beginning. Here we go. Quick rundown. This Monday is your midterm. It's in the syllabus. It's going to be from 1 till 3. It's going to be on the first 5 weeks' work, including what we've done this week. When you're finished doing the test, your test will be on WebAssign. When you're finished doing your test, you will write, well, you'll already, I'm assuming, doing it anyway. You'll write down all your working, and then you will take a picture of it using a program called Adobe Scan, and you'll learn how to use that. And because I've got a picture, a video on Canvas that will show you how to use it. It's free, you can download it for nothing and you can use it on your phone. And you will upload into Canvas, and I've got a video on how to do that right after the test. And I'll be here during the test, so there'll be a Zoom lesson during the test. So if you get stuck on something, you can just ask me about it. And I can hopefully talk you through the process to get it done.
Yeah, sounds good.
Sounds good? Midterm, this Monday. Big, big, important thing. That in your final is half your grade, right? So you don't want to take it lightly. And homework has to be done by this Sunday because of that. And homework is chapter 6. Right, I think I've covered everything. We're good now? Bye-bye, guys.
Thank you.
You're welcome.